Okay, hello everyone. So I'm Sumit Gulwani from Microsoft, and I'm going to be talking about test cases being more interesting than code itself, compared to what the pitch in the last talk was. So this is the paradigm where people are going to write test cases and the code is going to be automatically generated. So the traditional customer for our community has been a software developer. But today, there is a new opportunity, or rather should I say a new responsibility that presents itself to our community, is to serve the needs of end users who are 2 orders of magnitude more than the number of software developers in this world. So it turns out that 99% of people who have access to computational devices do not know programming. And they want to be able to write small scripts to automate repetitive tasks that they come across. So one option is to insist that they be trained to become programmers, or the other option is to actually provide them some domain-specific expert systems that can help them with their tasks. So what is it that these people typically struggle with? So in order to study this, I actually went and looked at help forums. So this is, for instance, what I figured out on spreadsheet help forums, where a person asks an expert on the community to give them a script that can, for instance, transform this input string on the left side of the arrow to the output on the right side. The expert looks at their example and tries to conjecture what their intent is and gives them back a macro to automate this. So in this case, the expert thinks that the user wants to extract 2 characters starting with the 5th one. So the user takes this macro, runs it on their data in their spreadsheet, and figures out that it does not do a good job on this other input, and sends this example back to the expert. The expert looks at it again and conjectures that maybe what the user wants to do is to extract the first substring that occurs between underscore characters. And this is the macro that he gives them back. So the user tests this and is happy with the result and sends a thank you to the expert. Now this interaction takes place over a course of several days. And we can actually automate it. We can automate the part of the expert where this interaction can actually take place in a few seconds. And this is the technology that we built, which was a paper that appeared in Popple 2011. And this is a feature that appears in Excel 2013. So I'm going to show you a demo of this feature. So here I have a collection of social security numbers in the first column. Suppose you want to format them by inserting hyphens, as you see in the second column. So if you do not know programming, then you will have to do this manually, which can be very time consuming and error prone. And even if you know programming, you will have to know the Excel programming model. But now Excel 2013 carries a feature called flash fill, which can be used to automate such tasks. So all that you have to do is to give an example as I have given and press Ctrl E, which will invoke this tool, which will look at this example, generalize it into a program, and run that program on the rest of the data in the spreadsheet to give you the output that you want. Now the Excel team, I think, did a good job at the user interface here. So suppose I want to extract the last name, and I give an example. And imagine you don't know that this feature exists, so you would not remember to press Ctrl E. So all that you do is to start typing the second output, and the moment you do that, the computer guesses that you have a repetitive intent in mind, and it auto-fires this feature. Now it is too good to be true to read the mind of the user from just one example. So sometimes you might need to provide more examples, as this scenario would illustrate. So here I have a bunch of medical billing codes, some of which have the right bracket at the end, like row 6 to row 10, and some of which don't. If your goal is to clean this data by inserting right brackets wherever it is missing, so let's see how the computer tries to guess your intent. So if you give one example, then the computer comes up with the simplest explanation, which is to add a right bracket everywhere. Maybe this is what you wanted, but otherwise you would observe that row 6 to row 10 are incorrectly transformed. So you can fix any one of these rows. And the moment I fix the second row, it is like giving a second example to the tool, and the tool can better converge to the intent that I have in mind. So you can use this to extract, let's say, relevant fields from huge strings in column A. So all that you have to do is to give an example each. Now imagine how much time it would take you to think about the logic and the Excel program that you'll have to otherwise write. So the tool can also learn quite sophisticated programs. So in this case, I'm learning a loopy program. You may or may not have spaces. You may put them in reverse order. You may use dots and so on. So this is something that we did a few years ago. And since then, we have been studying this space of data wrangling, which is the process that is used to transform data from a semi-structured format to something more structured. So it turns out that data is locked up inside various kinds of formats such as text files, log files, web pages, PDF documents, XML formats. So all these documents make it easy to visualize the data, but they don't make it easy to manipulate and analyze this data. So a typical data wrangling workflow involves extracting data from its existing semi-structured format, maybe possibly transforming it, which is the kind of thing that I just showed you a demo of, then querying it and maybe reformatting it. So data scientists typically spends 80% of their time doing these kinds of data wrangling tasks. And we hope that programming by example can provide a much easier and faster route to doing these, as opposed to writing scripts. So here is what they teach in a data science class, a famous data science class which is offered as a MOOC from Brown University. Suppose you have a document like this, which is taken from Wikipedia, and the goal is to convert it into a CSV format on the right. So as part of an assignment, the instructor provides people with a script to begin with and to build on top of this script to do this transformation. Now let me show you a better way to do this. So I've loaded up that file inside this tool, and all that I will do is to actually give examples of the data that I want to extract. So I'll give a couple of examples of the name of the championship. And when I do that, the system now tries to learn a program which, when run on this text file, will output a list such that the first two elements inside that list will be the examples that I provided. So usually it's very fast, so I don't know why my computer is behaving a bit too slow now. Now let's say I want to extract the year. So in this case, I will need to give only one example, and the system will learn by intent, because in the previous interaction there was already a model of the document that it started building. Maybe let's say I want to extract the winning score. Now in this case, when I give one example, the system tries to identify other such winning scores, but didn't get the third one right, because it turns out that there is a different kind of dash or hyphen being used here. So again, all that I have to give is to fix this example. And when I do that, then the system can better converge onto the intent that I have in mind. So this is a tool called Flash Extract, and it is shipping as part of PowerShell in this new version of Windows. And this technology was described in a paper that appeared in PLDI last year. So how does these techniques actually work? So at the heart of all of these tools, we have a search algorithm which tries to find a program that is consistent with the examples that the user has actually provided. Now, what is it that the user is providing me? The user is providing me some form of example. So let's try to understand what is the notion of examples here. So canonically, examples are supposed to mean some pairs of input states and the corresponding output value that you want to generate. So this is a canonical notion of examples that is used in the programming by examples community. But our notion is something more general than this. So we generalize the notion of examples in two ways. So one generalization is that the user is not giving me the concrete output on a given input state. The user is specifying some property of the output. Because output properties are often easier to specify than giving the full output. So for instance, look at this address file where I have a bunch of address records. So I would like to ideally be able to highlight, let's say, the names of 2 people, and I would like this table to be constructed on the right side by the tool. So we can do this inside our tool. Okay. So in this particular case, what is it that the user has provided? So the input to the program that is generated is the entire text file, and the output is actually the table on the right side. So if the user were to provide me the exact output, there is nothing else for the computer to do. So what the user is telling me by means of highlighting 2 green records is some elements that belong to the output list. In fact, the system might learn a program which might go and highlight elements that are not desired, in which the case the user can also provide negative examples. In fact, the user can assert something more. The user can say that the examples that I have provided to you are actually a contiguous subsequence of the output list, or even more precisely, a prefix of the output list. So these are all the properties that we can very easily exploit inside the search algorithm. Then the other generalization is that the user simply does not provide conjunctions of these constraints, but sometimes we might also be able to want to handle some Boolean combination of these kinds of constraints, that in a given input state, certain output property should be true. This usually arises as part of how we actually approach or solve this problem. So I will leave out any further discussion on this particular topic. So this is the problem definition that we have, that the user provides us an inductive specification, which is a Boolean combination of pairs of the form on some input state, the output should have certain property. And our goal is to find a program that meets such an inductive specification. So now this search, if I were to start, let's say, enumerating all possible programs of increasing size, is just not going to work, because the state space of programs is infinite. So what we do is we provide or we search for these programs over a well-crafted domain-specific language. And then the search space is relatively much smaller. So these domain-specific languages have to be defined or designed very carefully. So on one hand, they need to be expressive enough to capture a wide variety of tasks that the user wants to do in that particular domain. On the other hand, they need to be quite restricted so as to be able to enable efficient search. Furthermore, they should have operators which should have a small set of inverses, and I will explain this further when I talk about the search algorithm. And these patterns that the domain-specific language allows should also be quite natural, because this language is not just for the computer to program in. The users might even want to look at the programs that have been synthesized. This can help increase users' confidence. We can also have user interaction models where the user can select between different programs, or the user can even take a program that has been synthesized and edit it. And I will show you a demo of such a user interaction model later on. So let's look at the domain-specific language that we use inside the first tool that I had demoed to you, which was flash fill, or even inside flash extract. So in case of flash fill, one of the core tasks that arises is to be able to extract a substring out of a string. And in case of flash extract, you want to be able to extract a list of substrings out of this huge string, which was a text file. Now you might think that a regular expression might actually suffice. But the problem is that such a regular expression would actually be quite difficult to synthesize in the first place, and also be very difficult to explain to the user. So we have come up with some higher level computational patterns to be able to do these kinds of tasks, which are a good replacement for regular expressions. So our abstractions actually involve using much simpler regexes to do the task. So for instance, in case of flash fill, the domain-specific language that we use is that we try to compute a position inside the input string and another position inside that input string, and take the substring that is between those two positions. In fact, we can also do a relative offset. So the first position might be computed using some language which I am going to show you, and the second position can be computed as a relative offset of the first position. And you can make this domain-specific language even richer. Now the position expression, which computes an index into the string, can either be a constant offset, or it is specified by this PROSE construct, which takes as input two regular expressions and an integer k with the following meaning. So it evaluates to that position inside the string s such that the left side of that position matches with regex 1 and the right side of that position matches with regex 2, and it is the kth such match. So now let me actually show this visually to you what is happening here. So let's say I have this substring operator which takes as input two position expressions, and each of the position expressions, let's say, is not a constant index into the string, but is specified by these regular expressions or the pause operator that I just demonstrated. Then visually it looks like this. So I have this string S, then P is such a position such that the left side of P matches with R1 and the right side of P matches with R2, and similarly P prime is such that its context matches with R1 prime and R2 prime, and W is the substring in between. So this kind of substring language has some very interesting properties. So there are two very special cases. So if the regexes on the corners are epsilon, that is, they don't constrain anything about this context, then you're really describing the properties of the substring that you want to extract. On the other hand, if R2 and R1 prime are epsilon, then you're really describing the boundaries between which you want to extract the substring. And in general, we can have all of these four regexes being used, and you have a very powerful substring extraction operator. Now let's take a look at the domain-specific language that we use for the second task, which arises in flash extract, where we don't want to extract one substring, we want to actually extract a list of substrings. So common abstraction is, in the case of text file at least, is to split the file by lines and then select some set of lines using a filter operator. Then you map those selected set of lines to substrings within those lines using a map operator. And the domain-specific language for the filter expression can, for instance, say that I want those lines that have a certain regex, or I want those lines such that the previous line matches a certain regex. And the language for the function inside the map operator can be the same substring language that I just showed you earlier, the same substring operator. So there's an art to actually defining these domain-specific languages such that they remain expressive on one hand, and on the other hand, they also allow for efficient search. But even this restriction to domain-specific languages is usually not enough to build the efficient search experiences like the demos that I was showing you. So what we need to do is to model or exploit the properties of the operators in this domain-specific language in order to build smart search algorithms. So our search algorithm is basically built on the philosophy of divide and conquer. So the problem of synthesizing a top-level expression in a domain-specific language is reduced to the problem of synthesizing its sub-expressions. And it is a top-down strategy as opposed to a bottom-up enumerative search, which can try to construct all expressions in increasing order of their size and try to figure out which expression works. So this enumerative search is not going to work in this setting. And the idea in this divide and conquer, which constructs these sub-problems from the original problem, the way you reduce the original problem to sub-problems depends upon the inverse semantics of the operators that occur inside these expressions. And I'm going to show you two instances of this. So consider this task of extracting these yellow regions within this address file, and the user has given me two examples of these yellow records or yellow fields, and I want to figure out more such yellow fields. So in order to synthesize a program that can do this task, I reduce this specification for the top level DSL expression, which maps a string to a list of substrings, to constraints on the Boolean function and on the substring function. So as you can see, this domain-specific language for flash extract really involves splitting the file into a bunch of lines and then selecting some lines within those. So what we want this Boolean function to be able to do is to select those two specific lines which are bordered by these red rectangles. And then the substring operator that is used inside map should be such that it should map these red lines to the yellow regions inside them. So this is the kind of divide and conquer strategy that is at work here. Similarly, if you figure out how do we try to generate a substring program which can map the string Redmond comma WA to Redmond, we split this into sub-problems, and the sub-problem here is to learn a position expression inside a string. So the first constraint for the first position expression is that in the string Redmond comma WA, it should evaluate to the index 0, and the constraint for P2 is that in the string Redmond comma WA, it should evaluate to the position just after D of Redmond. Now, the second challenge in designing such algorithms is that the intent that the user has specified is highly ambiguous, because examples are an ambiguous form of intent, it's an under specification. So now if you insist the garbage in, garbage out philosophy, these systems are not going to be very usable. So the challenge here is to really guess what is it that the user is trying to say by giving very few examples. So the strategy that we use is that instead of generating or synthesizing one program, we synthesize lots of programs and we rank them. So this ranking function is based upon defining a partial order over expressions in the underlying domain-specific language. The two basic principles that we use are that we prefer smaller programs, so that when the user gives examples of the form I1, O1, I2, O2, then we don't just end up learning a conditional which says if the input is I1, then the output is O1, and so on. But learning the shortest program also will not always suffice, because if you remember the flash fill demos, I was often able to learn the intent from just one example. So the user gives me I, O, I can learn the shortest program print O, which is also not going to work. So you want to prefer programs without constants. So this is a simple basic ranking scheme. It turns out that this is still not good enough for usability. We need something much more sophisticated, where we use a linear function, weighted function over some program features, and these weights are learned using some machine learning techniques. And when we use this more complicated ranking functions, then we are able to bring down the average number of examples that are required in the basic ranking scheme from almost 4 to 1.5. And this is what was very important for the Excel team to be able to make a decision to ship out this technology. So let me just show you how good our ranking scheme really is here. So what do you think I'm trying to extract in column B? The first character, right? And what would be your guess here?
First two characters.
First two. And building on what you said, here you probably think the first three. But what do you think I'm trying to extract here?
The first name.
The first name, right? And this is what the system does. But if I really wanted the first 4 characters, all that I have to do is to give one more example, and then the system will actually fix it. And here I'm trying to extract the initial, and the system gets it right. So it figures out that the lower f here does not come from these lowercase f's, but it is a lowercase versioning of this capital F in the system.
I have a question.
Sure.
What if you try to extract the second letter of each word?
Could you repeat the question into the microphone?
Does that work?
Yes, so I can try to do those things. And
I'll repeat the question. What if you try to extract the second letter of each word? Does that work?
Let's see if it works.
But of both words?
So it seemed to
Oh,
work.
it does?
There.
Oh, okay, perfect.
Right. So I can try more of these tasks, right? But the good question to ask is, for what kinds of tasks would the system be able to do and it will not be able to do? Where does the boundary lie? So underneath this system, there's a domain-specific language, and if the task that you want to do fits within the domain-specific language, the guarantee of the search algorithm is that it will ultimately find that program with sufficient number of examples, and we try to use good ranking schemes to make the number of examples small. If the task that you want to do does not fit the domain-specific language that we have, then the system will try to fail and will say, sorry, the program is not possible to be synthesized from the constraints that you have.
So what is the training set for the machine learning algorithm? Is it the user's program, or is it some you've developed some heuristics and they ship with the program?
Yes. So this is the latter. So machine learning is not being used here. So here we use a technology called program synthesis, which searches for programs using the search algorithm that I described in this divide and conquer manner. There's no machine learning being used. Machine learning is used to construct these magic weights over the program features, and these weights have been learned in an offline phase. And the training data for that machine learning system look like something like this. Oh, on this particular input file, if the user gives me these 3 examples, then these are the other things that I want to extract. So that becomes our training data. So I want the ranking function to be such that I can quickly get a program from even 1 example instead of 3 examples.
Where did that training data come from?
Me looking at help forums and finding real tasks.
Could you repeat the question?
Yes. So the question is, where did that training data come from? I spent 3 weeks building an initial prototype of this tool. I spent 3 months trying to figure out the pain that end users have by looking at help forums.
Excuse me, I have one more question.
Here's the microphone.
Okay, I have one more question about the limitations, because all you show here was some kind of extraction of the data. What about operation of it on a data? So I don't know, with the example that you show, for example, if I want to, let's say, change some names and surnames, or just
Yes,
spell it in different, from left to right.
So we have built 10 different tools of this kind. Each tool has its own domain-specific language that is specialized to doing tasks in that domain. The first demo that I showed you was more towards transformation tasks. It generates functions whose signature is string arrow string, or more precisely a tuple of strings to a string. We have also done some work in the space of XML transformations, which I think is very powerful in general. The next demo that I showed you was an extraction related task, and if for time permitting, I'll show you another demo as well for a tool that reformats the data inside the spreadsheets. So ranking is a good mechanism to reduce the number of examples that the user needs to provide, but it is still not a foolproof mechanism. And we have to really think firsthand about what is the debugging experience that we will provide in this new programming paradigm. So John Walkenbach, who is one of the famous authors of this Excel textbook, actually warned about this, that you might think by looking at few cells that the system got the right transformation, but let's say if you're working over a sensitive spreadsheet and a few cells actually have the wrong entries, then it would be quite bad. So we have invested into building some good user interaction models for resolving the ambiguity that the user has in their specification. So one is that, of course, we make it easy for the user to inspect the output of the tool so that they can provide more examples. But even more interestingly, we actually show programs that has been synthesized to the user. And we convert these programs into English, because these people probably do not know programming. We let people select between different programs that we have synthesized. In fact, we also have an active learning model where we ask questions to the user, did you mean this or did you mean that? So let me quickly show you a demo of these capabilities. So here I have a bunch of citations that I have copied and pasted from a PDF document. And suppose my goal is to figure out who is the most cited author in this list of references. So as you can see that each reference consists of a list of authors, followed by the paper title, followed by the year in which the paper occurred. And after giving 2 examples of top level blue records, the system goes and extracts other such blue records. And you can see this pane on the right side. This is supposed to make it easy to, this gives you a bird's eye view of the document and supposed to make it easy to figure out where things went wrong. So there are 2 white regions here which are unexpected because these records are supposed to be contiguous. So the system didn't get it right. But if you fix one of them, then the system will go and also fix the other one. So now let's say I want to extract the list of all authors, and I give one example. And the system then goes and highlights other such entries, and the system did not get it right in the second record. Now if I give one more example, then the system will get it right. But what if this error occurred somewhere in the middle of the document? So let's see what is it that the computer is thinking. So the computer says to extract the green field from the blue record, you extract the substring starting after the first white space. So when I hover over white space, it shows me where that white space is in the document, which looks right because each record has a number at the beginning and a white space after which the list of authors start. And then it says that the green record should end at the camel case in the second line, which happens to be the case. So camel case is uppercase followed by lowercase. So it happens to be the case for the first record, but it need not be the case for every record, which is something that I know from my higher level knowledge of what this document is. So I know that this part of the program is actually incorrect. The ending logic of substring is actually incorrect. If I click on this arrow, then I can ask the computer to actually show me other highly ranked alternatives that it had generated. In fact, the next highly ranked alternative is the correct one, which says the first dot after camel case. And when I click on it, then the system shows me the right behavior. Now when I looked at this task, as a programmer, I thought this task was not possible to do, because I kind of guessed that the green region should end at a dot, But there are lots of dots inside the green region. There are lots of dots outside the green region inside this blue record. But the system was able to figure out one such logic that works, which is it is the first dot after camel case, because these dots that occur inside the green field are actually after uppercase. Now I can go further and let's say figure out here. And if I give one example, then the system thinks that I want to extract the first number before a dot, which is not really correct. Because this is a page number. If I just click on it, it is a signal to the system that this is not correct. The system then goes and tries to get the next highly ranked program and uses that. And now it changes the program to last number before a dot, which is the right thing. I can even go and extract nested data. So let's say I want to extract this list of authors individually. So by giving a couple of examples, the system will now be able to generate this structured data. Which you can easily transform it into JSON or any kind of other format that you want, and in a tabular form we display it like this. So we have developed lots of So we have developed lots of tools along this model. I showed you 2 demos. Then we have developed tools which can understand semantics of strings, like if 3 is March, then 4 ought to be April, and so on. The version inside Excel will not be able to do such transformations. We can do other kinds of transformations such as rounding and formatting numbers. Now imagine whatever language you are programming in, you have to remember the format characteristics of even formatting, let's say, numbers or dates. But examples are a natural way of expressing intent. We can even do much more complicated tasks like text normalization. We also have developed a programming by natural language technology for doing querying, such as how many people make more than average in a given payroll spreadsheet. You can ask queries like that. We have also done some technology on reformatting tables, on automating repetitive tasks, let's say inside your PowerPoint slides. But I'm going to show you another demo of something which is more significant, which helps you extract data or reformat data within spreadsheets. So after some kind of more non-trivial processing from the citation extraction demo that I showed you, you might end up in a situation like this where I have the number of citations for each author in a given conference, and let's say I have this data for multiple conferences here. And now I want to figure out who is the most cited author across all of these conferences. Now if this data was in a proper structured tabular format, I can use tools like Power BI or write SQL queries, but the data is not really like that. So I can actually tell the tool to construct me a table with 3 columns, and I can give examples of entries that should be there inside this column. So this is my first example, and then I can give an example somewhere down below to make it more representative. And then the tool will try to learn a program which can generate a table which is going to have tuples of the kind that I have provided. And now I can do queries over this structured table. So this is a tool called FlashSlate. It appeared in PLDI this year. This one does not ship yet, and we need to figure out the right way to actually put this out. So a note of thanks to my collaborators. So Alex Polozov is the one who has built this framework over which we have constructed these different synthesizers. So this is the divide and conquer search algorithm that I showed you. Then Dilip and Rishabh have worked on FlashFill. Wu worked on FlashExtract. The rest of the authors here worked on FlashRelate, and Mikhail and Gustavo really built this nice UI that I actually showed you. I didn't have time to talk about natural language processing though, which is something that Mark led. You might imagine applying this technology to other domains. I think in a couple of decades when household robots become more common, this will be a fantastic technology to program robots. You can imagine integrating this inside existing programming environments, because this can be useful even for developers. And ideally, the intent should be expressed using combination of examples and natural language, because sometimes tasks are easier specified using natural language, such as reduction tasks like average, filtering, and so on. So I'll conclude here, and I will actually just have the sales page that we are hiring.
And we have time for questions.
This is amazing stuff.
One more time.
Sorry. This is amazing stuff. What is the patent status of this work?
So Microsoft owns all the patents in this space. I've been doing this work at Microsoft Research for the past 5 years, and we do have patents on most of it. Microsoft owns it.
No more questions. Here you go.
Are you going to give this as some kind of library to be used, for example, in .NET or something like this, or would be only for?
Yes, so the flash extract and slightly reduced form of flash fill also ships as part of PowerShell, and different MVPs have created their own UI experiences on top of it. We hope to be able to release more such APIs that can be pluggable inside different user experiences that people have. The other question to ask here is that what is the kind of programs that we generate? So we generate these programs in our cute little functional languages, but these programs are easily translatable into any other language that you want, and that's a much easier task. It's a simply syntax-directed translation. But if you care about producing the smallest program, the cute little program inside Python, then it is going to be a more sophisticated problem, and we'll have to do a proper search over those programs.
We have a few more minutes.
What about performances and much big data when you show?
Yes, so the tool works much faster than what I was able to demo here. Unfortunately, there's something wrong on my machine. If you want to, so there's a team that is also shipping out this technology that cares about analyzing log files, parsing and analyzing log files, which is important for ensuring agile software development. And there, the scripts that we generate need to be run on gigabytes of data. The programs that we generate are typically, they run in size, time linear in the size of the data. We even generate streaming programs. So the real cost is in synthesizing those programs, which fortunately only depends on the amount of data over which you give examples, which fits in a screen. That is quite real time, as the demo showed.
Here you go.
You've mentioned analyzing logs, and that's why I have another question. Because the other thing that I would what comes to my mind when I am analyzing log and some machine learning at the same time would be Apache Spark with Spark streaming and machine learning based on Spark. So how did you test it? How is going the performance? What's the difference in performance in these two approaches? Yours approach and Apache Spark?
So I do not really know what they do, but there's a difference between using machine learning to draw insights and analytics on your data. And what these tools do is to help massage the data into a form in which machine learning can be applied in a more easy manner. So in a typical life of a data scientist, they are spending 80% of their time in just massaging this data from one format to another format and bringing it into a form that can be easily consumed by machine learning algorithms.
Okay, but what's with a situation in which you get new data all the time, and at some point the program might, for example, think, okay, no, I was doing it wrong. Maybe I should do it different way.
So let me answer that question by asking you a question. Right? How would you write a program in such a setting?
Well, I'm not sure. I think
How do you know your program is correct? You write test cases. And here you only write test cases. However, you can do better. Once we extract data or do any kinds of transformations, we can actually analyze the data that has been extracted. So the functions that we synthesize are partial functions to start with. So for instance, the function might be extract the third word inside the string, and then I get a string which has no third word. So I can raise an exception at that point of time. Or I can, let's say, but all strings have third word, but let's say I get a different kind of a string which seems to extract alphabetic characters as opposed to years. And if I have some semantic knowledge of data types, I can again raise a warning. And these are the things that we are planning to invest into now. But debugging is a very important thing for this programming model to take over, and we have to think about first-class treatment for debugging. I don't think so I have the perfect answer to that question, but we are starting to invest more and more into this.
Just a small question on the UI. Is there a way for the user to prevent the adjustment on the second example? For example, let's say everything is correct, but just one thing is off, and you don't want the system to learn from your second adjustment. Is that possible today in the UI?
So the user can correct the examples. So they can, if they override any one of the highlighted examples, it will undo the assumption of the original highlighting.
Right, but what I'm saying is, let's say you make one example and the system has learned and then filled the rest in the flash fill example.
Yes.
Let's say every row it guessed correctly except for one.
You can then go and manually fix it.
But if you manually fix, is there a chance the system will learn from your second fix and make adjustments that...
In case of flash fill, the way this technology has been exposed is that once you do the learning thing, there is no memory of what happened before. It is as if you just type the data yourself. But you can imagine other user interaction models which is watching for any data to change and then refire. That would be a different kind of user interaction model.
Okay. Thank you.
Thank you very much.
Which can be very time consuming and error prone. And even if you know programming, you will have to know the Excel programming model. But now Excel 2013 carries a feature called flash fill, which can be used to automate such tasks. So all that you have to do is to give an example as I have given and press Ctrl E, which will invoke this tool, which will look at this example, generalize it into a program, and run that program on the rest of the data in the spreadsheet to give you the output that you want. Now the Excel team, I think, did a good job at the user interface here. So suppose I want to extract the last name, and I give an example. And imagine you don't know that this feature exists, so you would not remember to press Ctrl E. So all that you do is to start typing the second output, transform this input string on the left side of the arrow to the output on the right side. The expert looks at their example and tries to conjecture what their intent is and gives them back a macro to automate this. So in this case, the expert thinks that the user wants to extract 2 characters starting with the 5th one. So the user takes this macro, runs it on their data in their spreadsheet, and figures out that it does not do a good job on this other input and sends this example back to the expert. The expert looks at it again and conjectures that maybe what the user wants to do is to extract the first substring that occurs between underscores characters. And this is the macro that he gives them back. Of software developers in this world. So it turns out that 99% of people who have access to computational devices do not know programming. And they want to be able to write small scripts to automate repetitive tasks that they come across. So one option is to insist that they be trained to become programmers, or the other option is to actually provide them some domain-specific expert systems that can help them with their tasks. So what is it that these people typically struggle with? So in order to study this, I actually went and looked at help forums. So this is, for instance, what I figured out on spreadsheet help forums, where a person asks an expert on the community to give them a script that can, for instance, okay, hello everyone. So I'm Sumit Gulwani from Microsoft, and I'm going to be talking about test cases being more interesting than code itself, compared to what the pitch in the last talk was. So, so this is the paradigm where people are going to write test cases and the code is going to be automatically generated. So the traditional customer for our community has been a software developer. But today there is a new opportunity, or rather should I say a new responsibility that presents itself to our community, is to serve the needs of end users who are 2 orders of magnitude more than the number. So the user tests this and is happy with the result and sends a thank you to the expert. Now this interaction takes place over a course of several days. And we can actually automate it. We can automate the part of the expert where this interaction can actually take place in a few seconds. And this is the technology that we built, which was a paper that appeared in Popple 2011. And this is a feature that appears in Excel 2013. So I'm going to show you a demo of this feature. So here I have a collection of social security numbers in the first column. Suppose you want to format them by inserting hyphens, as you see in the second column. So if you do not know programming, then you will have to do this manually.